Hi everyone, start to look at our kinetics work now. Now remember, if you remember from way back in the start of the semester, I said 1 or 2 is basically 3 topics, right? So it's yes or no, will a reaction happen, which is thermochemistry, which we'll meet later. Equilibrium, which is how much stuff will I make, and this one, kinetics, which is how fast will I make it. So kinetics is all about, if you think about the word kinetics, it kind of implies speed, right? So chemical kinetics is about how fast reactions go. Now some reactions can be over in a femtosecond, like things, you know, on the scale of photochemical reactions, for example, happen on the femtosecond scale, whereas, you know, things from nuclear decay, which we'll study later in the course, can happen over thousands of years, all right? So reactions can be either really, really fast, or really, really slow, or somewhere in between, okay? Now, in our lab, of course, we'll look at ones that are on this, you know, half an hour to 3 hour time scale because, you know, that's our lab time. But be aware that, you know, reactions can be as fast as you like, really, or as slow as you like. Okay. Now, let's get into some kind of simple ideas, right? So, what things affect the rate of a reaction? Okay. Now, if we think about it, what must happen on the microscopic level to make something new? Okay, so we can kind of draw a little picture, right? I love these pictures, right? So if we have a chemical equation, now remember from you know, the very start of the semester, I told you that a chemical equation was really a microscopic description of an event on the atomic scale, right? So if I have something simple like, you know, A2 plus B, maybe we'll put them in the gas phase for reasons we'll talk about, turns into A2B. All right, so there's a balanced chemical equation, right? What might, and we'll talk about reaction mechanisms later, if this was a very simple, what we call unimolecular step, just the things bumping together, what would that look like on the molecular level, right? So we'll put it down here, molecular level. A2 might be like a diatomic, you know, like that, right? And that literally bumps into an atom of B, right? And it turns into, maybe it's something like that. Okay. All right. I feel like those two bump into each other and they turn into that product. All right. So there it is. So there's our kind of, and I'll keep doing this, right? Keep banging the reactants together. As we'll find out, it's all about the reactants bumping into each other that causes a reaction to happen. If you think about it, it's very simple, right? If these two things didn't bump into each other, I could have never made this product. And kinetics, in a nutshell, is just how often they bump. That's what kinetics is. Okay, so let's write that down. So we'll write it here. So molecules, now I'm going to put a little asterisk there because, you know, they can be molecules, they can be atoms, they can be ions, some microscopic particle, right? Molecules, and they have to be either in the gas or aqueous phase. Now that's important, right? So molecules, atoms, ions, either in the gaseous or aqueous phase because they have to be able to move. If they're trapped in a solid, they can't really move, right? So we like to think about solutions and gases, right? Okay, so that's where reactions typically occur, right? So molecules in this, either in the gas or aqueous phase must, here's the key word, collide in order for our Rxn is my code for reaction to occur. So let's just read that, okay? So molecules, either in the gas or aqueous phase, put a little dot there, must collide, and we call that, when they stick, we call that a fruitful collision, which we'll talk about more later. So atoms, molecules, ions in the aqueous or gas phase collide and stick, we call that a fruitful collision. Their sticking product, if you like, is the product of the reaction, okay? Now, easy way to remember this, right? Show you a silly picture, right? So those who took my 101 know this story, those who didn't don't. So I'll tell you anyway. Right? So this takes you back to the 1980s, right? So in the 1980s, Britain had its once-in-a-generation soccer star, this guy here called Paul Gascoigne, or Gaza, right? Because all the soccer stars who are any good have one name, Maradona, Pele, Ronaldo. Right, so Gaza was our once in a generation star. He played for Tottenham Hotspur. He was the captain of that team, captain of the England team, really talented. Right? Okay, this is a very famous picture from the 1980s where this is Gaza, right? Outside of Stringfellow's nightclub in West London at like 3 o'clock in the morning. And you're like, well, so what? But the thing is, he has a game the next day, right? So someone actually ran into a pharmacy. This is the 80s, no phones, right? So went into a pharmacy, grabbed one of those disposable cardboard cameras, snapped this shot, sold it to the Sun newspaper for $100,000, right? And the next day, you know, there's Gaza with his gyro, right? The next day he had a terrible game, and you know it's all through the newspapers. You know they were hounding him, right? No, it's kind of funny because Paul Gascoigne really liked to live life in the fast lane, right? And so he would be out drinking until late at night, and he'd party all the time. And you know what happens when you do that? Well, you get a little fatter and you get a little slower, right? So eventually he drops out of the England team. He gets a little fatter, gets a little slower. Eventually drops out of the Tottenham team, right? And we see a similar thing here. So what happens when the Cubs have a player that doesn't cut it anymore? They send him to Iowa or something, right? What happens in the NFL? Well, they send him to Canada or something, right? So there's always some lower team they send them to next when they're not quite cutting it in the pros. And we have a thing in England, it's called Scotland, right? So we send all the Premiership players who aren't any good anymore to finish off their careers in Scotland. And here's Gaza playing out his career, and there's the effect of the Euros, playing out his career with Glasgow Rangers. Okay, so this reminds me of my favourite saying. Chemistry, atoms bumping into each other, is a bit like Scottish soccer. It's just a bunch of round things bumping into each other. Okay, that's what chemistry really is on a microscopic level. Things bump, do they stick, yes or no? If they stick, you make a new product. Good to go. The more often that happens, the quicker the reaction is, the more stuff you make per unit time. Okay, so moving on. Enough of Gaza, right? So, interestingly, not all molecular collisions result in a stick, right? Okay. Some fraction will be like, so it's all about where the molecule gets hit, right? Not just the energy it gets hit with. And that's called when it has, you know, we'll get onto it later, but when they do stick, it's called a fruitful collision, right? So some fraction of molecular collisions in just the right spot will be fruitful. So some fixed fraction of molecular collisions will be fruitful. These fruitful collisions then result in the formation of a product, okay? So what we're doing then when we kind of speed up this, how fast a reaction goes, we're just making the number of fruitful collisions per second higher, right? Okay, so simple question. Okay, now if you ever get stuck with kinetics, always come back to the simple idea, right? Collisions amongst the reactants, right? So quick question here. What would happen to the rate of reaction, i.e. how many products you make per second, right? The speed of the reaction, if the number of molecular scale collisions were increased. So if you had the number of collisions per second increase, would it go faster or slower? You know, right? Faster. More collisions per second, more fruitful collisions per second, more product per second. If you slowed them down, right, slow the molecules down, less collisions per second, slower. Okay, so slower rate of reaction if the number of collisions is decreased, faster rate of reaction if the number of collisions is increased. And that's the basic microscopic fact I want to keep in your head. Don't get confused later on with all the math. It always comes down to a simple idea. How often do the reactants bump into one another? Okay, and there are things that affect that, obviously, which we'll talk about. Okay, but your fundamental microscopic fact is this, right? Okay, the rate or speed of a reaction depends on the rate of collisions among the reactants only. Once you made a product, doesn't matter, you made it, right? It's all about the reactants bumping into each other. The more often they bump into each other, the more often they have a fruitful collision. Fruitful collision results in the formation of a product. This is your basic fact, right? Basic micro fact. Okay, so always keep that Simple idea in your head, more collisions per second amongst the reactants, more stuff I'm going to make. Okay, now we don't live on the microscopic level, right? We can't go down there and start manually bumping molecules together, okay? We live in the macroscopic world, the world of big, right? So what kind of lab scale variables do we have which would ultimately result in the reactants moving and bumping into each other more often, okay? So before we go there, just remind ourselves what we're doing here. So same as here to here. This is the key, right? Sorry, this is the key fact. This is the trick. Same thing, really. Always remember that the speed or rate of a chemical reaction is directly proportional to the number of molecular scale collisions happening per second amongst the reactants, right? Some fixed fraction of those will be fruitful. Okay, so how then do we speed up the reactants? Well, let's just rephrase that. What can we do to get more collisions per second amongst the reactants, right? Think about it. There are actually 4 things you can do. So think about it. Think about going into a lab and just pause me for a second and just think about it and write it down. I'm just going to write one word next to each letter and each number, right? 4 things we can do to make a reaction go faster. Or if we do the reverse, make it go slower, right? Got it? What do you think? Number 1, concentration. Yes, if you increase the concentration of the reactants, the reaction will go faster. Okay, talk about why in a little bit, right? But if you increase the concentration of all the reactants, it will definitely go faster for reasons we'll discuss, right? Number 2, maybe this is a little bit out of left field, a little bit. There's things out there called catalysts, right? You actually have one in your car, right? In your car exhaust, right? A catalyst is kind of an outside agent that will make a reaction go faster. And the key thing about a catalyst is it's not a reactant, right? It's a pseudo-reactant, meaning it makes it go faster, but it doesn't get used up, okay? The classic example is the platinum palladium catalyst in your car. It just basically provides a surface where the reactants can kind of find each other, and so therefore they bump into each other more often on this surface, and it's a faster rate of reaction. But again, we'll get to that in a moment. So that's concentration, presence of a catalyst. Okay, the one you're all thinking is this one. Temperature, right? The hotter something is, the faster the reaction goes. This is why you're in a fridge and a freezer, right? So if you think about spoiling of food, yeah, that's a chemical reaction, biochemical reaction. If you put something in a fridge, the spoiling reaction takes maybe a week, right? Put it in the freezer, maybe it takes 3 months. Leave your bacon on the counter, come back a day or 2 later, it's no good, right? So those microbial reactions, which are chemical reactions, right, complex ones, but they're chemical reactions, the warmer the temperature, the faster they go, yeah. So temperature is a big thing in terms of rate, yeah, and we can monitor obviously how hot or how cold something is in the lab, all right? So temperature is a big one. And finally, last one, maybe you know this, right? So if you've ever been out for a nice dinner with your parents or something, and you go to some really fancy restaurant and they bring out like an after dinner coffee and those big clumps of sugar, right? Not granulated sugar like in a packet, oh no, some big old kind of cube of sugar, right? And you're stirring it forever, it takes forever to dissolve, right? Because it's got a relatively low surface area. So if you've got a solid, the more surface area it has, the faster it reacts for reasons we'll talk about in a moment. Okay, so there we go. That's our 4 big variables for making things go faster in terms of a reaction. Concentration of reactants, the presence of a catalyst, the temperature the reaction happens at, and if a solid's involved, its surface area or relative surface area. Okay. Now, it's going to take them in turn, right? So number one I think was our concentration, right? Now, remember the microscopic fact, right? The more collisions per second, the faster the reaction goes, right? Okay, how would concentration change the number of collisions per second? Well, a nice way to think about this is to think about a game of pool, right? Okay, so you can play 15-ball pool or like 9-ball, right? So let's pretend you break off with the same kind of speed or energy in either game, right? Which break, a 15-ball or a 9-ball, would result in more ball-on-ball collisions? So think about the balls a bit like reactant molecules, right? The more often they bump together, the faster the reaction is, yeah? So What causes more ball-on-ball collisions? Well, obviously the 15 ball, right? Because you've got 15 balls flying around the table rather than 9. So there's going to be more collisions amongst 15 things in the same space than there is 9 things in the same space, okay? And that's what's really happening. So what concentration does, as you increase the concentration, you decrease the distance between particles, right? So if you decrease the distance between particles and they're all moving at the same speed, aka same temperature, there's more hits per second because they're closer, right? So concentration, if you increase the concentration of all the reactants, you'll definitely increase the rate because there's more collisions per second because the reactants are closer physically in space, right? Okay, so let's write that down. So more, yeah, if you got a good handle on that, write your own thing in the box. But I'm writing this. More reactants per volume results in more collisions per second, right? Therefore, faster rate of reaction. So therefore, increasing concentration of reactants increases rate of reaction. Okay, so simple idea. The more concentrated the reactants are, the more collisions per second because they've got less far to go to bump into another reactant, faster rate. Okay, nice and easy. So that's the concept there, right? So it's an easy concept. Lots of our labs, well, 2 of our 3 or 4 kinetics labs will be changing the concentration of reactants, okay? And there's a nice little experiment we do called an initial rate, which we'll talk about as we go. All right, next one, catalyst. As I mentioned, a catalyst is something that speeds up the rate of reaction without getting involved chemically, right? So it doesn't turn into something else. It's not a true reactant, it's a pseudo-reactant. So if I look at the definition from the definition from the dictionary of a catalyst, I'm just going to copy my notes here. A substance, so catalyst is a substance that increases the rate of a reaction without undergoing chemical change itself. Okay, so you can harvest the catalyst, right? So this is why that when they recycle your car, they carefully remove the old catalytic converter, which is worth about $300, and they take it off just to be cleaned, and then they use it again, okay? Because the catalyst doesn't actually chemically change. Sure, it's going to get dirty, right? But just clean it off, you can use it again, okay? So a catalyst is a substance that increases the rate of a reaction without undergoing a change itself. It just helps the reaction go faster. And we'll talk about the energetics of that later. It's kind of interesting. But if you think about, your car catalytic converter, that's a good example. Okay, some books like to say the word consumed, right? So the catalyst is not consumed like a reactant would be during the course of a reaction. Okay, they can be heterogeneous. Hetero means different, of course. So you can have like a solid catalyst with a gas reactant, right? That's what happens in your exhaust in your car, right? Or homogeneous. So, for example, you might add H plus ions to a solution. Changing the pH to a lower value may increase the speed of the reaction, which is kind of interesting. Okay, so catalysts can be same phase or different phase to the reactants. Okay, got a little note to myself here. Do you own a catalyst? Yes, you do. We mentioned it. It's in your car. Okay, all right. Oh, talking of which, there is a catalyst from your car. Okay, so that's a cutaway of the catalyst from your car. All right, so you can see it's kind of like, it looks like, if you take it out, it's a ceramic sponge essentially. And you look at it and you think, well, sure, it's like a ceramic sponge. It's kind of really light, low density because it's mostly empty space. It's very, very porous, right? And you look at it and you go, where's the metal? And it's interesting because we'll talk about relative surface area soon. The smaller the particles of platinum and palladium that are in there, it's called a platinum-palladium catalyst, a byway catalyst. the higher their relative surface area, right? So if you kind of finely divide something up, it's got a higher surface area, right? So it's really, really tiny particles of platinum and palladium in the catalyst, and they're so small you can barely see them, but they are in there, okay? All right, so the platinum palladium catalyst, the new car muffler, is a two-way catalyst. It's called two-way because it does two reactions at the same time, okay? So it gets rid of the two unpleasant gases which a car can create, right? So if a car isn't working properly in terms of its combustion, it may be kind of like not using enough air, like, you know, making CO, or it may not be hot enough and it may be making like nitrogen monoxide instead of nitrogen and oxygen, right? So let's look at that, right? So the two horrible gases that can come out of a faulty car engine or exhaust system are NOx, which is nitrogen monoxide, nitrogen dioxide, right? Just NOx for short, right? And CO, carbon monoxide. So that's a poison, and that's smog essentially, right? This is why cars get smogged in California. They're just making sure the very low amount of these come out of the back, right? Okay. And if you remember those pictures from the 90s and the 80s of like Los Angeles had that kind of brown kind of cloud over it, that's smog. Okay, that's nitrogen monoxide, nitrogen dioxide. All right, so what happens is, so we don't want these as byproducts of our reaction. So what happens is in the catalyst, 2CO plus oxygen from the air, gas, in the presence of the catalyst, palladium, platinum, turns into 2CO2. All right, a less harmful gas, right? Okay, and finally, 2 nitrogen monoxide gas. They kind of bump into each other when we make N2 gas and O2 gas. Fair enough. Now, how does the catalyst work? Well, in simple terms, we talk about energetics later, but what it does, it provides a surface for the reactants to meet, essentially. Yeah. So if I said to you, hey, meet me in the Sears Tower, and you get to the Sears Tower, and then you spend like, you know, half your day trying to figure out what floor I'm on. There's 100 floors, and you kind of search each one until you find me, because you're looking in a three-dimensional space, right? So the building is a three-dimensional thing. But if I was a little bit more specific and I said, hey, meet me on the 27th floor, it wouldn't take you long at all to find me, would it, right? And if you think about it, if the molecules are confined to a flat surface rather than the three-dimensional space, their relative concentration is relatively high, isn't it? Because they're closer together. So things, you know, marbles rolling around on a tray are more likely to hit each other than, you know, those in a giant kind of space, right? So by providing a flat two-dimensional surface, 2D surface, the concentration is kind of pseudo-increased, right? So the concentration of the reactants goes up because they're in 2 dimensions, not 3. So that's one reason why catalyst works. It's the surface, but not the only reason. We'll talk about more as we go. Okay. Now, third of the 3, okay, so concentration is super important. We'll do reactions with concentration changes. And then we kind of like, you know, it's Hatfields and McCoys, and then we kind of leave that alone, right? So concentration experiments are done at a fixed temperature, right? And then we look at the effects of temperature at a fixed concentration, right? So that's called the Arrhenius work. So that's in a future packet, right? So packet 2 will essentially be concentration terms, and packet 3 essentially will be temperature terms, right? So the big two is what I'm saying. The big two are concentration and temperature. So let's look at the temperature now. So why do things spoil when you leave them out of the fridge, right? Why does it happen so quick, right? Okay, so what happens to the rate of molecular collisions and therefore the rate of reaction when the temperature goes up? Well, the temperature is really measuring what for a molecule? It's measuring its speed, right? So if the molecules are moving faster, they hit each other more often, okay? So hey, speed is proportional to rate, and temperature is related to speed. All right, so let's write that down. So the speed of molecules increases with temperature. Now, it's interesting because it's not a linear thing. It's actually an exponential thing, right? So T is proportional to speed squared. Energy for an object is half mv squared, right? So velocity squared is proportional to energy or temperature, right? So the more energy they have, the hotter the temperature, the speed goes up a lot, yeah. So that's why things spoil at even a slightly higher temperature, yeah. So the difference between the outside world and the fridge is only 20 degrees, yeah, sometimes, maybe 30, right? That's nothing in the big scheme of things, but it can make a huge difference in terms of the rate of reaction because there's an exponential relationship. And when we look at this in lab, a tiny difference in temperature can make a big difference in rate. And there's a reason for that, right? There's a reason for that exponential relationship, and we'll discuss it. It's the Arrhenius/Boltzmann math, right, which we'll get to. Okay, so therefore, more collisions per second at higher temp, therefore faster rate. So we're back to that same old thing, right? There's more collisions per second amongst the reactants because they're moving faster, okay? So concentration and temperature essentially give you the same result, don't they? Concentration, they're closer but they're moving slower, so they still bump together quite often. Temperature, they're further away but they're moving faster, right? So they still bump together more often. Okay, so if we can kind of write ourselves a little note here. Increasing temp always increases rate of reaction. So the rate of a reaction always increases as temperature goes up. The rate of a reaction will always decrease as temperature goes down. That's why we own freezers. All right, and there's some little math there. So the kinetic energy of a molecule, an atom, an ion, is proportional to its temperature, right? So kT, right? T is temperature, kinetic energy is the energy of the molecule, right? K is just the Boltzmann constant. And then, hey, if I put that in terms of the speed variable, temperature is proportional to velocity squared. So the rate of reaction changes with velocity squared then, okay? All right. Finally, and I'll do it real quick because I've got like 2 minutes, right? The surface area of a reactant is super important if it's a solid, yeah? So if I get actually I'll just do it with my hands, right? So here's my two hands as one object, right? If I cut my two-handed object in half, look, it's now got much more surface area, right? So if you take a brick and you keep cutting it into smaller and smaller pieces, it still weighs the same, right? Even though you cut it up, all the pieces weigh the same as the original brick. But there's much higher surface area because every time you cut it, you expose more surface, yeah? So that's why powdered things have a massive surface area. That's why the particles in the catalyst are so tiny, right? And you see this when you go to the mall, right? If you ever go to the mall and go to Gloria Jean's whenever we get back there, you see these swizzle sticks with kind of crystalline sugar, yeah, and you're supposed to stir your coffee with those. So if you've ever bought one of those coffees and you're there for hours and the coffee gets cold before the stick dissolves because it's got a very low surface area. It's just a blob of sugar, right? However, if you take powdered sugar, which they use in baking, right, because it dissolves instantly, and they use powdered salt, pickling salt is just regular salt, real fine, right, because it dissolves instantly. Why does baking sugar and pickling salt dissolve almost instantly? Because they got super high surface areas because they're super fine, okay? So, just write down, powdered solids have relatively high surface area. So if you think about it, when you're trying to dissolve something with a high surface area, it's more collisions with the solvent per second, right? Therefore, more collisions per second, therefore, faster rate reaction. And there we go, time is up. So I just about finished just in time there, okay? So let's stop, I'll come back in a second and we'll talk about defining the rate of reaction, right? How do we get some math on this? So we got the idea of the colliding particles, collisions per second, rate of reaction. How do we get math on that? Okay, so I'll stop there and come back in a second. Okay, so if we just kind of summarize our findings from the last couple of pages, right? It's very, very simple. How fast a reaction goes, how many moles of product you make per second, right? It's completely dependent on how many fruitful collisions per second happen amongst the reactants. Because hey, if the reactants stick to make a product, how many times that process happens per second That's the rate of reaction, isn't it? Okay, so what we'll see with our math is it all really comes back to that microscopic fact, right? So, simple questions first. How do you know, because you know you're in a lab, right? How do you know a reaction is occurring or is finished, right? So just think about something simple. Think about sitting outside and firing up your grill, right? How do you know when that reaction is finished? Because the charcoal's gone. It's all turned into CO2, right? So we can monitor with our eye the disappearance of the charcoal, right? And we know to put more charcoal on there when it gets low, right? So we can look at the disappearance of reactants. So the reactants will disappear with time. Or, which is more likely what we'll do in an experiment, we'll look at the appearance of product, right? So as one goes, it turns into the other, right? So reactants turn into products. We have this kind of synergic, one goes up, one goes down relationship, right? So let's write that down. You see appearance of product and or disappearance of reactant over time. So that's how you know, right? And when you've got no movement, right? So when there's no product being formed anymore, it means you must have run out of reactant. If you can't see any more reactant, you made the maximum amount of product. So once it's finished, you got the maximum amount of product, no reactant. Okay, so if we think about it, how do we put a speedo on our reaction? How do we measure the rate of change, right? So speed, right? So if we think about a car, speed in a car equals distance over time, right? How many miles in 1 hour? 1 mile divided by 1 hour will be 1 mile per hour, right? 60 miles in 1 hour would be a speed of 60 miles per hour, right? So that's how we define speed. Rate of change of distance in time. So how do we define speed for a reaction? Well, we're not going a distance, we're actually making stuff, right? So it's amount products formed per time or amount reactants lost per time, okay? So that's what reaction rate essentially is. How many moles of stuff do I make per second or per minute, whatever the unit is of time, right? How many moles of stuff do I lose per second or per minute? That's, you know, products and reactants in terms of their respective appearance or disappearance, all right? So that's what our definition of reaction rate is. So in the box, let's write something specific, right? So the rate of a reaction equals change. So if you think about it, it's going, if it's a product, it's going from nothing to maximum, right, over time. And if it's a reactant, it's going from maximum at the start to nothing over time, right? So it's the change. And I'm going to put a little plus here, right, because it's always going to be increasing for products, right? So change in product concentration per unit time, okay, how long it takes for 1 mole to appear, right? Or we can look at the disappearance of reactants. So we can look at the formation of product or the disappearance, so minus, so it's going away, change in reactant concentration over time. There we go. Those are our two simple word definitions. We can look at one or the other, right? So in an experiment, typically maybe you'll have either a colored reactant or product, which you can pick up with a colorimeter, right? Okay. Or maybe you're changing the pH or something like that. So there's some telltale sign of a reactant or product appearing or disappearing, which you can monitor with a machine, right? Okay. Believe it or not, when we do this in lab, we like to use iodine because iodine is a nice purple color. So if iodine is a reactant, which it is in one of your experiments, it disappears in time, and you just kind of watch the beaker until it's clear and colorless, right? And you just kind of press the stopwatch because your eye is the best color detector ever made, right? Okay, so if we get a bit more mathematical with that, if we turn those words into an equation, right? So if I think, hey, rate of reaction equals, well, if I think of change in reactant concentration over time, right? So I'm going to go minus, and instead of writing the word change, what's change in math? It's delta, right? So change in concentration. Now concentration is just square brackets, right? So we put square brackets around something. That means it's concentration. Reactants, right? We'll put formulas in there later, but just generically. Change in the concentration of reactants, and minus, because they're getting lower, reactants always go away over time, over the change in the time it takes to do it. Ah, okay, fair enough, right? Fair enough. The minus is somewhat optional. You know, I like to do minus because it reminds me they're going away. Okay. Or it can be the change in the product concentration with time. Okay, so if I go back, just kind of show you that one again. Change in product concentration over time, change in reactant concentration over time. I'll just put it into kind of a math version of that, right? And those are your equations, right? So I'll write it here too. And again, you can use either one depending on your experiment, which reactant or product can you essentially see, right? And that's be the one you'd measure. And we'll go into that in a second down here, and that's called measuring the rate with respect to something, yeah? So reactants and products, their speeds of formation and disappearance are all related based on stoichiometry, which we'll get to. But we generally just pick one of them and say, hey, just thinking about this one, just thinking about oxygen, say, or whatever it is, right? What's the speed with respect to? Just thinking about that one thing, okay? All right, so let's see that now. So here's the reaction, yeah? So here's a balanced chemical equation. Two of these, you have to excuse my phone, two of these molecules fall apart to make four of these and one of those. As we'll see later, the stoichiometry is important, right? And we'll kind of do a little bit of intuition on that in a little bit, right? But what we can do, we can just turn this generic form here into something that relates to these individual reactants and products, right? So if I was looking at O2 in this system, right, it's a product, right? So it's going to appear with time, right? So the rate with respect to O2, just thinking about this one, right, it's going to be the change in concentration of O2 over the time taken to make it, right? Fair enough. Now think about these in isolation, right? Say I couldn't see oxygen. Maybe I can see NO2. NO2 is smog, it's a brown color. That would probably be the one we looked at, right, if we did this experiment. If I'm just thinking about NO2, it's a product. It's just a different formula. I know your spider sense is tingling, right? You're saying, well, why isn't it 4 times this one? It actually is in terms of numbers, yeah? So because I make 4 of these for every one of these, it looks like I'll get 4 moles for every 1 mole, which is true, right? So in the reaction, this will make 4 times as much as this. But we're not looking at that ratio now. We're just saying which one are we looking at right now, just one of them. And we'll talk about how they relate to each other later. That's called with respect to. So if I'm looking at something with respect to NO2, I'm only thinking about NO2, right? And that's the definition from up here, isn't it? Okay, so be careful there, right? Okay. What's the old phrase? Don't run until you know how to walk. Okay. Can you write this one? Be careful though. What's the rate with respect to N2O5? All right, got it? Careful, I'm going to put a negative because it's a reactant. It's going to go away in time, right? Change of N2O5 with time. All right, so change in concentration with time for each thing taken separately. That's a definition. Okay. Yes, they relate to each other, which we'll get to later through stoichiometry. So the numbers relate. But for now, those are the definitions. All right, now, more math, right? So there are different ways we can express the rates of reaction, okay, and we'll talk about them kind of in progression, right? So we'll talk about the easy one first and then look at kind of more and more challenging ones. All right, so first one, what is the average rate of reaction? Well, it's very simple. The average is just the average over the entire course of the experiment. If the experiment takes 20 minutes, what's the average speed over the entire 20-minute period, right? So our time, delta T, will be the entire length of the experiment, and our change in concentration will be, you know, the maximum change of reactant or product in that time. So it's a very simple one, right? So here's a very simple worked example. If it takes 32 seconds, right, to see the appearance of 2 moles of O2 from the previous example, what's the average rate of reaction, okay, of formation of O2? All right, now be very, very careful, right? So we like to use moles per liter for gases and solutions, right? Because if you think about it, how many moles in a liter, it doesn't matter if it's a gas or a liquid, does it? Right? Or a solution, I should say. All right, so what we're going to do, we'll always use moles per liter. Moles per liter for gases, moles per liter for solutions. All right, so it's always going to be moles per liter. So concentration will be in moles per liter, and seconds will be the time here, okay? Then we've got a 1 liter container, how nice, right? So we've got 2 moles of gas in 1 liter, so that's obviously a concentration of 2 moles per liter, isn't it, at the end? Because it's a product, right? We make 2 moles. All right, so calculations, careful. Change is always defined as the final minus the initial, right? And this seems trivial right now, but later on it's important to always follow that procedure, right? So if I want the change in concentration of oxygen over the change in time for that happening, right, I got to make sure I'm correct in terms of final minus initial. So that's what's written here, yeah? So the change in concentration or time is the final value minus the initial value, all right? So for O2, it's a product forming, right? So the final value is, hey, 2 moles per liter, right? So it's final concentration of O2 minus initial concentration of O2, right? Which equals, it's a product, we end up with 2 moles per liter minus, now where did it start, right? Well, it was a reactant, so at time 0, when we started this reaction, it hadn't made any yet, right? So reactants always start at a high number, products always start at 0. Okay, so 0.0 moles per liter. Now that's trivial because, hey, obviously it went from 0 to 2, the change was 2, but we have to show that, right? It won't always be that simple, which equals 2 mole per liter. Change in time, well, final time, the experiment took 32 seconds, right? I'll just write it down, 32 seconds. And we all start at time 0, so when we start, say go, it's time 0, right? So it is trivial, it's 2 moles in 32 seconds. That's clear from the numbers, but they're easy numbers, right? So why don't you just figure it out? What's the average rate of reaction, right? It's 2.0 moles per liter in 32 seconds, which equals 0.063. Now careful, interesting, the units of speed for a reaction are always the same. Moles per liter per second. So you can write moles per liter per second, or m minus 1, second minus 1. When you put it to the power of minus 1, it's just 1 divided by, right? Okay, there it is. All right. So the units of speed will, I move that up. The units of speed will always be moles per liter per second. If they don't cancel out to moles per liter per second, you're not doing the calculation right. Okay. Next one. Now, do you think the reaction goes for the same speed from start to finish? The answer is no, right? Okay, the answer is no. Okay, and there's a great analogy here. Okay, so the analogy is driving from Joliet to Chicago, right? Okay, so let's talk about the analogy and then see how that kind of exactly maps onto a real equation, right? Or a real rate of reaction problem, right? So let's say you're driving to Chicago. It takes you 1 hour to drive to Chicago. Fair enough, right? So you did 60 miles in 1 hour, 60 minutes, right? So that means your speed, your average speed was, average equals the total distance over the total time, 60 miles, 1 hour equals 60 miles an hour. That was your average speed for the whole journey, right? Okay, but now let's be honest, right? Were you traveling at 60 miles an hour the whole time? No, as you get closer to Chicago, the traffic gets kind of worse, right? So you slow down. Eventually you find Wrigley Field or wherever you're going, right? And you're moving like maybe 10 miles an hour looking for a parking space around Wrigley, yeah? So you get progressively slower as time goes by. It's kind of interesting. You're progressively making more product, but you're doing it at a slower rate, okay? So the reaction slows over time, even though you're adding a little bit more every second, okay? So that can, you know, imagine this, right? So you get on the expressway right outside the college. It's open, right? You're traveling at 70 miles an hour. So instantaneously, in the first part of your journey, you're traveling at 70 miles an hour. If I said to you, if you look down and look at your speedo outside the college when you're on the expressway, it says 70, right? And then as time goes by, traffic gets congested, you get to the outskirts of Chicago, and maybe you're going on 30 or something, or maybe 40 miles an hour. You get to the, you know, the expressway start to merge and all that. 40 miles per hour. So at some point in your journey, this is the thing I'm talking about, at some point in your journey, and you glance down at the speedo, you have an instantaneous speed. What's my speed right now, right? Outside the college, instantaneous speed is 70. Closer to the city, look down, instantaneous speed's 40, right? And the average is, you know, 60 over the entire journey, right? Okay, so how does that analogy work with our actual chemical systems? Well, think about it for a second. Think about it for a second, right? Remember this? The more collisions amongst the reactants per second, the faster the speed is, right? Okay. Think about it. When are the concentration of the reactants always the highest? Right at the beginning, yeah? So if you think about it, right at the beginning of a reactant, we haven't made any products yet, so we haven't used any reactants yet, so they're the highest concentration. They bump together, stick, and form a product, right? So if you think about it, their concentration will diminish over time. So over time, in every reaction, the concentration of reactants diminishes. Hey, their concentration goes down, less collisions per second over time. So reactions always slow down. Their speed always slows down, just like driving your car to Chicago. The speed of reaction will always slow down the further towards the end it gets, okay? That's because the concentration of the reactants gets less over time, okay? Less collisions per second. So let's write that down. The rate of reaction always slows, this is assuming we're at a fixed temperature, right? Over time, like driving to Chicago. So the analogy is a good one, right? Because, why don't you fill in the rest, right? I'll write mine in a second. The rate of reaction always slows over time, just like driving to Chicago. Your speed always slows when you drive to Chicago. Why? Different reasons, but why? Concentration of reactants decreases with time. Therefore, number of collisions per second amongst reactants decreases with time. I'm going to read it because my writing's horrible. Therefore, slower rate of reaction. So let's just recap that. How would you expect the instantaneous rate, so you're measuring the rate at some point in time during your journey, right? So how would you expect the instantaneous rate of a reaction to vary through the course of any reaction? What molecular events are responsible? So the rate of any reaction always slows over time, right? You make more stuff, but at a slower rate. So you might be making 10 moles per second right at the start. You might be making half a mole per second near the end, right? So you're always making more, but it's just happening at a slower speed. Yeah. Why do you make stuff less fast towards the end of the reaction? Why does the rate of reaction slow? Because you're using reactants, you're turning them into products. Therefore, the concentration among the reactants diminishes over time. They bump into each other less often then, if there's less of them, concentration effect, rate slows. Okay, hopefully that makes sense. All right. So, what we can look at here is a generic graph which kind of puts all that into perspective, okay? So honestly, I mean, all reaction rate graphs, the raw data always looks the same. This is the one for reactant, right? We'll look at ones for product later, but if you think about it, reactant, you're going to start at the maximum and then it's going to decrease over time. And eventually it's going to become stable, right? So that's essentially zero there, isn't it, right? When it's finished. Okay, so that's the maximum amount of reactant, that's the minimum, and it takes this amount of time for it to go to zero from its maximum, yeah? And we always get that exponential looking decay there. It's not linear, it's exponential, okay? Now, what are all the points on this graph? Well, let's do the easy one first, right? So E, line E here, if you think about it, E is a line, and if I look at the slope of that line, think about this for a second, right? Speed is what? Speed is change in concentration over change in time. It's rise over run. Have you heard that phrase from a graph, right? So the gradient of the concentration versus time, concentration divided by time, moles per liter per second, is the speed. So if you remember one thing from this page, speed equals slope. Okay? If I find the slope, I find the speed. So the average speed is just, hey, what was the total change in concentration over the total change in time? It's line E, isn't it? It's the slope of line E. Slope of E equals the average rate or speed of reaction, right? Okay. Key point, right? So the slope of concentration versus time is the speed. Okay, if I'm just doing the gross average, right, the whole change in concentration over the whole time, like our average was 60 miles an hour to Chicago, right? Okay, it's over the whole time. So it's, you know, essentially modeled by this line, isn't it? The slope of this line, start to finish, change in concentration, change in time. What's that average speed or slope of that line? Fair enough. Now, we're not really interested in the average, right? We're interested in the instantaneous speed, right? So here's the thing. So what I can do, and you can see it here, 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 and here. What the graph is trying to show you is the tangent to the curve. So if I have a curve like this, right? If I draw a tangent at that point, that gives me the gradient at that point, doesn't it, right? So whatever that point is in time, be it this point in time, this point in time, or this point in time, time zero, I can find the slope at that point in time. That's the instantaneous, the speed of reaction, the slope at that point in time, right? So A, if you look at A here, now this is something a calculator would do, you've kind of extrapolated because you can't, let's actually look at this one here. If I look at B first, yeah, if I want to figure out the slope of that point, I kind of draw a symmetric line either side, don't I? I kind of use my eye to draw a line that kind of looks to be kind of equal both sides in terms of that gap, if you like. That gives me the slope at this point, yeah? However, I can't really do that for time zero, so I got to kind of try and extrapolate as best I can. Now, a computer can do that, we can't, right? So A is the tangent to the line right at time zero, right? We call that the initial rate, okay? So the instantaneous speed at time equals zero is the initial rate. Okay, very important, right? So that's kind of an important point. Every reaction has a start, right? So that's the one we always compare between reactions, right? So the slope at t equals zero equals, we'll just call it, is the initial rate. Okay, the initial rate is an instantaneous rate. It's just special because it's recorded at time zero. Okay, and that's the slope of the line A there. Okay, so if you wanted to kind of draw that line, you'd measure this distance, divide it by this distance, rise over run. It's very steep. It's the steepest of all the lines on there, isn't it? Because it's the one right at the start. Remember, there's most concentration in reactants right at the start. So hey, initial rate's always the fastest, the steepest line. Okay, and then B and C and D, B, C, D, instantaneous rates at times B, C, and D. D's kind of, if you think about it, D's kind of trying to go there, isn't it? So D is kind of, you've picked 2 points and gone between them. We'll talk about the math of how you choose, you know, what the slope is measured at, right? So if I can go between points, come down, or I can kind of, again, that's the same, between points and come down. Here it's flat, right? So I can just pretty much draw a flat line there, okay? So B, C, and D are instantaneous rates at particular points in time as given by markers on the graph B, C, and D, okay? Now, if you notice, as time goes by, that's steep, that's less steep, that's flat, that's a slope of 0, right? So over time, the slopes get less, that means the speed gets less, yeah? But through time, I'm always getting less reactants, yeah? So eventually I get down to 0 reactants and 0 speed. So when I got 0 reactants, I got 0 speed, maximum reactants, maximum speed. And it's an exponential decay over time. Okay, but again, key rule here is, remember, rise over run. We draw our tangent line, change in concentration, change in time, divide those two lengths if you like. That'll give us the speed at that point in time. Okay, that's kind of hard to do for time equals 0. We kind of extrapolate that one, but we can get an idea. Okay. Oh, I'm going off the bottom. Let me show you that again. It's kind of hard to see the graph and the words, so I'll just go through it one more time. So E is the average, we talked about that. A is the slope at time equals 0, okay, the initial rate. B, C, and D are the instantaneous rates at those 3 points in time. Okay, hopefully that makes sense. Okay. All right, so I'm at 27.25. We'll just write this last thing in, and then I think we're good to stop for a second, okay? So, think about this, right? Actually, maybe I'll leave you with this question, and then we'll come back and do the last segment, right? The last 29-minute segment. So, discussion, if the concentration of reactants decreases with time for any reaction, right? I'll show you that. There it is, right? So, let me move that up. If you look at all those lines, right? Well, if you look at that line, if you look at the red line, concentration is always decreasing through time, isn't it? Okay, that's true for any reactant species, right? So, if the concentration of reactants decreases over time for any reactants, how does the concentration of products vary with time? How does the rate of formation of products vary with time? So, as we saw, right, it's steepest at the start and then shallowest at the end due to the relative concentration of reactants at those points in time. Okay, try and think what the graph will look like for the formation of products, right? If I'm losing reactants quickly, I'm making products quickly, right? But they're starting at 0 because there's none to start. So I'll do it on the side over here real quick. So if reactants look like that, products are going to look like that. Ah. And you kind of have this kind of almost like a mirror image situation, yeah? So that would be our reactant plot, that would be our product plot, okay? So let's write that down real quick. So, product concentration is always increasing. So if you want to think about it, it's like the mirror image argument to reactants, right? So reactants are always going away, products are always being formed. It's just the rate of their relative formation and loss is changing over time, right? So the product conformation is always increasing. Rate of formation decreases over time. All right. Bit of a camera malfunction there, so back real quick. So I actually filled out the graph down here before I noticed the camera had run out of time, but let's just recap what I just said. So if you think about it, it's kind of an obvious thing, okay? As the concentration of the reactants decreases with time, and I kind of showed you this on that previous graph, the concentration of the products always increases with time. We have this kind of nice mirror image graph, okay? So if you like, that's reactants. Reactants start their maximum decay to 0, products start at 0 and rise to their maximum, right? And that's when the reaction's done. So when those lines go flat, that's when the reaction's complete, okay? So here's my picture of that, okay? So in the box, draw a nice picture, okay? So generically, concentration of reactant or product up the side, time along the bottom, there's your product growth, there's your reactant decay. Remember, if you draw a tangent to that line at any point in time, maybe after 10 seconds or something, rise over run is the speed, okay? Change in concentration over change in time, okay? And there's a couple of just things out of the book there. So that's kind of products by itself, reactants by themselves, okay? Now, I just move things around here. What we're going to look at now is an actual example that uses that kind of logic, right? So here we have a reaction between hydrogen gas, so it's nice to have a microscopic view, isn't it? H2 and I2. They combine to make 2HI, okay? So there's our, and it's interesting, we'll talk about this later. If you just look at, they didn't show the I2 graph, they just showed the H2, right? So that's your H2, oh, move it up, sorry. So, just like that. So there's your H2 concentration dropping away with time. That's a reactant, okay? There's our product concentration growing over time. Now, interestingly, and again, we'll talk about this in a second just to confirm, but it kind of makes sense because you lose one of these from making two of these, it's a 1 turns into 2 ratio, right? So at any point in time, this graph here, or the line of this graph here will be at any point in time, we'll choose a time there, okay, 50 seconds. So for example, at 50 seconds, this slope we expect to be twice as steep as this slope, right? So the speed is twice as much for something that makes twice as much. That's a kind of a common sense thing, and we'll kind of mathematically explain that later. But that's what we expect, right? So features of the graph, kind of reactant, write it down here. Decay from max, and that would be here, right? Okay. Product forms from 0, and that's from there. And okay, and product forms twice the rate of reactant loss because of the 2-to-1 stoichiometry. 2 of these for every 1 of these. The gradient at any point in time, and we'll confirm this with math in a moment, the gradient at any point in time is going to be twice as big. Okay. Also, this will be a positive slope, if you like, because it's appearing. This will be a negative slope because it's disappearing. If we just throw in the numbers in the formula, we'll see that just comes out naturally. Okay. So, actually, if you look in the back of the packet, okay, in the appendix, I actually have that same graph, okay, and we're going to use it as a worked example. And I also have the data set, right? So, here are our times, which are along the bottom, okay, along the bottom, and our concentrations up the side. There they are, okay. So we have kind of a table of raw data, and whenever you do a kinetic study in lab, this is essentially all you collect. You just measure the concentration somehow of a reactant or product with time. So that's your raw data, and if you want to kind of put that in a box and say, that's raw data. And then the question is, well, how do we use that raw data to calculate rates, right? Okay, so keep this on the side. We'll come back and look at it as we go through. Okay, so calculating instantaneous rates of reaction. So in our example, it looks like we're going to use 50 seconds, right? So we're going to look at 50 seconds here and find the slope for reactants disappearing and for products appearing at 50 seconds. So again, have this kind of by your side, right? Okay. So remember, we need to figure out the slope at a particular point in time. All right. Now, to do that, we need to figure out the gradient, right? So at that point in time, figure out the gradient, okay? If you think about it, how do you figure out gradient in calculus? It's dy dx, right? Which is basically rise over run same as it is here, but it'd be D concentration over D time, right? For a very small increment in time, yeah. So you get kind of a very small separation of data points, and you find the difference between them, rise over run, that's your gradient. Okay, so that's calculus, yeah. We're not going to use calculus, but we're going to use the kind of the origin of calculus, right? We work out the slope by comparing, if you like, the difference between two data points. Okay, so two ways to do it. Okay, the equation of the line will be kind of a gross kind of calculus version. Look at 2 points on the line, kind of mentioned that, right? So that's down here in a minute. But the obvious graphical method is what we've already talked about, right? So you can, and you know, you don't do this unless you have experimental data plotted, right? Okay, on a test, you wouldn't have a plotted graph, right? You'd have the table, right? So on the test, you have the table. So we use the math method in a moment. But in the lab, you may actually have the, you know, the Lab Pro or whatever device you have plot the graph for you, right? Maybe you can print this out, yeah? And if you do the graphical method, again, you just draw the line of, you know, so at 50 seconds, draw the tangent line, and then you can work out rise over run by just kind of extrapolating out that triangle, all right? We can do that there. So let's actually take a look at that. So question says, graphical method, draw a tangent line to the experimental rate of reaction. Yeah, I just saw that. And then find its gradient by hand. Okay, so it wants us to do it for HI. All right, so let's look at HI. Actually, what I'll do, bit of creative origami, right? Bear with me here. Okay, so you move this up. There, okay. So what we're going to do, and I can make some space, yeah. So at 50 seconds where this line is drawn, we draw that tangent so it touches there, yeah, and then we have rise over run, okay. Now, remember how it works, right? So rate equals change in concentration of, in this case it's HI, right, over change in time, right? It's always final minus initial, right? So concentration first, because it's growing, right? And time runs this way, so final is always the later time, isn't it? So this point right here, right? So the concentration at the end, whatever that is, that's 1.5 something, right? So that's 1.5 something minus final minus initial 1. Actually, we can easily do it because it's nice and 1. So that is actually where that hits 1.56, isn't it? Because it goes from 1 up 0.56 to 1.56. So the final is 1.56 moles per liter. Initial 1.0 mole per liter. Okay, divided by, put it in brackets, time. Well, final time was, looks like 70 seconds, right? Initial time looks like 30 seconds. Move that up so you can see it. So it comes down here, 70, 30. Difference between 70 and 30 is 40, right? So that equals 0.56 molar over 40 seconds. And those are the two numbers that they've actually put on the scale, right? So it's 40 run, 0.56 rise. There it is. Divide them out. Don't have a calculator handy because I use my phone as a quick calculator. All right. So work it out yourself too. I'll just work it out on the side here real quick. 1.56 divided by 40 equals 0.039. Remember the units, moles per liter per second, right? Moles per liter divided by seconds. Okay, and if you like, you can put a plus in front because it's appearing, right? If you think about it, that makes total sense because when we put those numbers in our equation, it was the big number minus a small number, which will give us a positive number, right? So that's nice. So when we have a positive slope, that's a positive slope, isn't it, right? From bottom left to top right, it's always going to naturally give us a plus number. Okay, now what I want you to do Okay, what I want you to do, just for fun, okay, not for fun, for academic enrichment, okay, work out what the slope is here, okay, and we've predicted it'll be it'll be half as fast, right, because it's a 1 to 2 ratio, yeah, so basically, and our final position was in time here, yeah, whatever that is. Yeah, so we're looking at this gap here, which is 0.028, right? Okay, why is it 0.028? Because the final number pertains to this point, right? So that's around 0.2, right? And this number is whatever it is, right? So it'd be 0.48, right? So maybe we say, you know, I haven't got the exact numbers, but say that's 0.2 and that's 0.48, right? It's final. 0.2, so concentration change 0.20, which is the second point in time, right? Because time is linear, right? Ben Cisco, don't forget, right? 0.2 minus 0.48, which equals minus 0.28, right? So that's where they got that from, right? Okay, difference in time is 40 seconds. So divide them out, 0.28 divided by 40. Minus 0.28 divided by 40. We're going to predict it's half of this value, right? So it's going to be around 0.2, right? 0.02 rather. So 0.28 divided by 40 equals 0.007 minus. Close, right? With the rounding. Okay. So you get the idea. Okay, you get the idea. All right. Now, that's looking at actual tangent lines on curves, right? That's actual tangent lines on curves. Fair enough. All right. Okay. Next thing, what about using that table? All right. So remember I did my creative origami. Let's just do it again. So I have this next to you. There's a table, right? Okay. Now, hopefully you remember the equation of a line. So the gradient, right, of any line, m, equals rise. So that's y2, the bigger side number, if you like, minus y1 over the run, x2 minus x1, right? So therefore, we have our classic equation, y2 minus y1 equals m x2 minus x1. So we solve for m. So the gradient is the slope, okay? And we have two adjacent points. So if we go back here, that might be x1, y1. That might be x2, y2. And you got to keep it straight, right? You got to keep it straight. So the one that happens sooner is x1 and y1. The one that happens later is x2, y2, okay? And what we're going to do, we're not going to draw a tangent, okay, but we can get an approximation for that by taking 2 points that straddle where we want to hit. So we might take, let's actually look down here, we'll take the 40 seconds and the 60 second value, right? And then we'll find the gradient between them, and that'll give us the speed, right? So that's the idea. So we're going to use the equation of the line using straddling data points to find speed or rate, all right? Okay, so when we look back here, what do we find? Let's just read it and then look at it, okay? So there's our data set, right? Nicely, they've found the differences for us, which we'll look at in a moment, right? But we can do the differences ourselves, right? Okay, so move it up a bit, okay? Actually, I'm going to maybe have you guys do it after I've explained it, right? So we're going to use the equation of the line for two adjacent data points which straddle the time of interest, right? Call them equidistant data points, right? So that's what I'm saying here, okay? So let's do it for H2 at 50 seconds, right? So if I look down here, H2 at 50 seconds is there, right? So the adjacent data points are here and here. So x1, y1, x2, y2, all right? So that number and that number. All right, so let's figure it out, right? So let's just move that up, move it there. Actually, why don't you give it a go, right? So why don't you give it a go? So m equals, let's make sure up here, right? y2 minus y1 over x2 minus x1. The 1 will be the one closer in time, all right? Okay, so you work it out, right? So that's x1, y1, x2, y2. Okay, let's figure it out. y2, 0.301 moles per liter, minus y1, 0.44. Now that's interesting, right? Because hydrogen is a reactant, so it's decreasing over time. So it was more concentrated in the past kind of thing, which is here. Makes sense, right? And then when we subtract this from this, it'd be a negative number, which is what we want. It pops out. Okay, so you should always naturally get a negative number for changing concentration when you're doing a reactant. That's a nice tip, right? And finally, time's always going to be positive, right? So the final time is 60 seconds. Initial time's 40 seconds. And remember, those are the two data points that straddle the time of interest, yeah? Okay, which equals, let's figure it out. Hopefully you got this one. .301, oh, clear. 0.301 minus 0.449, oh. Equals, hang on, 0.301 minus 0.449 minus 0.148 moles per liter. 60 minus 40, I think I can do that. Divided by 20, 0.279 moles per liter per second. Okay. Hopefully you got that. 0.279 moles per liter per second. Okay. Oh, move it up, sorry. So it's kind of hard to get them both on the page. Let me just recap that. So the gradient, and what we're doing is, I'll just show you. We're manually finding the gradient at 50 seconds, right? Here. Oh, is that 50 seconds? Yeah, that's 50 seconds. We're manually finding by looking at this data point and this data point, drawing a line between them essentially with math, and then finding the slope, right? Okay, so that's x1, y1, x2, y2, all right? Okay, so stick the numbers in. There they are, and there's the answer. Okay, now, is it perfect? No, right? If you think about it, it should be, because we measured it at the same point in time, 50 seconds, actually, yeah, we measured it at the same point in time. If I go back to my original graph. Okay, so we worked out this one, but just by drawing the tangent, and that one was 0.039 moles per liter per second minus 1, right? And this one, well, it should be about half that, right? But it's 0.27, right? So it's a little bit bigger than half that. Why? Because the two methods are slightly different. Okay, that's not a, remember this is a curve that's exponential in shape, so it's not kind of equal heights different on both sides, if that makes sense. So it's an approximation. Obviously, the closer these points are, the better it will be, and that's essentially what calculus is, because dy dx is a little change, right? Okay. All right, so hopefully that makes sense. So two ways to do it. This one you do in lab, and this one you do in exam. Okay, so I guess my point is be familiar with the second method. So when you actually are given the table, like this one, and I think most of the homework questions are like that, you can actually, remember, linear time, right? So x1, y1 are the lower time, x2, y2 are the higher time. Okay, all right. All right, so next one. Wrap-up example. Hopefully you've got the hang of it, right? So let's read it. So consider our previous example, the one we just looked at, right? There's back to our kind of summary slide. Oh. I think someone from India is trying to tell me my Apple phone's out of date. Maybe you're getting those phone calls. All right, so here's our example we've been working with, right? Okay. What I want you guys to do is use this wrap-up example just to practice, right? Now make it worth extra credit. 2 points. Okay, so let's see what it says. So read through it, and then we'll talk about the assignment. So, as you'll discover in lab, most kinetic studies are monitored with time versus concentration versus time. So we get that same data set every time, which then gets plotted to give you a graph. Okay, so we have regular intervals in time. This raw data is then plotted to do the graph method, or just use directly from the table to do the line method, equation of the line method, okay? So you can, okay, do this, right, for a new time. So using the tabulated experimental data, that's this, okay, work out the instantaneous rate with respect to the disappearance of hydrogen. So that's the hydrogen numbers, of course, at 80 seconds. So you're going to have to do the straddling, do the 90 number, do the 70 number. Show me the math, so you can kind of send me back this one page with the math done here. Okay, maybe work it out, take a picture, email it, right? That's fine. Okay. All right. Have that, 2 points. Actually, I am changing the deadline for this. Okay, so I've decided, and I'll mention this in an announcement, I'm not getting many people come to office hour, right? And I think that's because they're still looking at videos. So I'm going to move the video deadline up till Wednesday. Okay, so video deadline and extra credit deadline will be Wednesday from now on through the rest of the semester. Okay, because then, if you do have an issue, you can come to office hours. Okay, not seeing anybody at office hours. All right. Okay. So extra 2 points by Wednesday of next week. All right. So remember the basics. The instantaneous rate of reaction is the measure of change in concentration over change in time, the gradient of the curve at that point in time. You get it either by drawing a tangent, rise over run, or by doing y2 minus y1 over x2 minus x1, rise over run. Okay. All right, next thing, we actually talked about it a little bit in that last segment, okay. I am going to run out of time, so I'm actually going to stop and come back real quick, okay. Now, we're going to start talking about that relationship we already kind of peeked at, right? So over here, we saw that, hey, because I make twice as many products as I use reactants in a 1-to-2 ratio, the slope at any point in time will be twice as steep for products compared to either reactant, H is the one being measured in this case, because hey, one makes two, twice as much stuff in the same amount of time as twice as fast, right? Okay, so we see that kind of come out in the kind of the shallowness of this curve, or if you like, the steepness of that curve. All right, and it all comes back to the stoichiometry here, yeah? Okay, so there's a definite relationship between rates and stoichiometry. So this is the trick. You find out the rate with respect to one reactant or product, right, in your experiment, and then because you know the stoichiometry, you can work out the rate of the other things by their ratio. Okay, so always work out with respect to first one reactant or product, and then look at the stoichiometry. So if it's twice as much, double. If it's half as much, half. Right. Okay, so we see that as we go through. Now, keep it simple to start. Just do a simple, if you like, you can put the numbers in. 1, 1, 1, 1. It's a nice, easy one to start, right? And then we'll go back to the N205 example. Okay, so question, is the rate of appearance of this equal the rate of appearance of this? Well, the answer is yes, because it's a 1-to-1 stoichiometry. 1 to 1, right? So if you like, the rate, if we did with respect to the appearance of C4H9OH, that one, because it's 1 to 1, equals that one. Fair enough, right? Now I've got a couple of very simple questions, right? Do something similar, but an answer here, right? So is the rate of appearance, sorry, is the rate of disappearance of the chloride equal the rate of disappearance of water? Well, yes, because it's 1 to 1 again. So write that mathematically, right? Give you a second, pause me, come back. All right, back. So rate, and you can put minuses in there because it's the disappearance, right? C4H9Cl equals, again, reactant, minus H2O. There we go. And then finally, you can do this one, right? So write the rate expression for a reactant and a product. Okay, they're both 1 to 1. So let's do that one. Rate equals it's going to be plus. I'll put a plus there, right? It's a product. There we go. 1 to 1, product, reactant. Okay, so those are all nice and easy ones because it's a nice 1 to 1 to 1 to 1. Okay, but what about where we have non-1 balancing numbers? Okay, so let's go back and look at that equation we had previously. 2 N2O5 makes 4 N2O and 1 O2, right? Now you can kind of use kind of logical kind of steps here just to kind of figure out in your head, right? But then we'll show you at the end it's nicer to use an equation, all right? Okay, so first things first, the rate of reaction can be expressed in terms of either this, this, or this. In a lab, we'd probably figure out the rate, a number of moles per liter per second of this guy, right? So we'd probably compare to that. And if we think about that, it's just in words, what's going to happen, right? It's a 2 to 4 to 1 ratio, right? So we're going to get this number from our plot. We get the slope at any point in time from plotting concentration versus time for this thing, right? Then, hey, if we wanted the concentration versus time relationship for any of the others, the rates for any of the others, we just look at stoichiometry. So to say this was, you know, keep the number simple, right? 4 moles per liter per second after 20 seconds, right? This would be 1 mole per liter per second, and this would be 2 moles per liter per second going away because it's in a 4 to 1 to 2 ratio. That'd be 4 times less, that'd be half, right? 2 times less. Okay. So simple questions then. We can express the rate in terms of any of them. We choose that one and then use stoichiometry to work out the numbers for the others. Okay, so simple question. Does NO2 increase at a faster or slower at the same rate as O2? Well, faster, as we said, by times 4, right? Because it's 4 to 1, right? So therefore, if I write this, so say we had rate equals, and we worked it out, right? NO2 delta time, right? So we get a number for that from our experiment, yeah? We get the slope at some point in time because we can measure this one. It doesn't equal, and I'm going to finish this in a second, O2. See, it doesn't equal the same number, does it? This is a quarter of this value, yeah? Okay, so here's the thing. You want to make the two things the same, yeah? So either I can put a 4 in front here, right? But let's keep apples with apples. Let's keep the 4 with the formula, right? If it's going 4 times as fast, and we're going to compare everything to 1, well, why don't I just multiply it by a quarter? Ah, there we go. So the thing that's 4 times faster, because it's 4 to 1, if I divide it by 4, it's now the same speed. And that's the trick, right? So you always divide the rate expression by the stoichiometric constant. Okay, now you know that. work out the relationship here. So question, does N2O5 decrease faster, slower at the same rate as O2? Well, it's 2 to 1, so it's faster by a factor of 2. Then you write it in, right? So rate equals what? This is called a rate expression, right? So write it in. Okay, what have we got? Well, it's going to be, I'll not put the numbers in to start, right? So it's going to be change in concentration of N2O5 with time equals change in concentration of O2 with time. But it's not equal because this is twice as fast as this, so I'm going to make it half as fast by doing that. Okay, so the stoichiometric constant comes in as a fraction. Okay, stoichiometric constant comes in as a fraction. If I express that whole stoichiometric constant thing generically, so for A of A, B of B makes C of C, D of D, you know, it's minus because it's a reactant going away. 1 over A times its rate, 1 over B rate, 1 over C, 1 over D. Okay, that's how we make them equivalent. Okay. Now, worked example, and people always get this wrong on the test because they think it's harder than it is. Okay, so if you see something like this on the test, it's super easy, right? Here's the Haber process, making ammonia, right? So 1 reacts with 3 to make 2, right? Express the rate of the above equation in terms of changes in concentration with time of all 3, right? So rate equals, it's going to be, this one's a reactant, so it's going to be minus, and there's one of them, 1 over 1. If you just, if you just left it, it'd be fine, right? N2 dt, right? So there's one of them. Okay, 3 of them here, which equals 1 over 3 minus, because it's reactant going away. And if you don't include the signs and everything, it's not going to be right, is it? And that's going to be plus, and there's 2 of them. There it is, right? So that's in terms of all 3, right? Okay. Now then, see if we can do this. I'll just give you the setup. I'll let you run it through. So when H2 is decreasing at this number, right? So therefore, delta, maybe this is the one we're able to measuring in the lab, right? It's decreasing, so that's minus, right? Moles per liter per second. Okay. How is this increasing, right? So we're just going to take this one and this one. So minus 1 over 3, change in H2 T equals plus 1 over 2 we just want this. We just want that, right? So you're just going to rearrange it. What are you going to get? What are you going to get? It's 2 over 3. And obviously, you know, sign here, it's going to be positive, isn't it, right? So this just goes over here, 2 over 3 times, let's just write it. So equals 2 over 3 H2 dt, which equals 2 over 3 times 0.175 moles per liter per second, which equals, let's see what this book says, 0.117 moles per liter per second. Okay, makes sense, right? If you think about it, if the H2, which there are 3 of, is disappearing at 0.175 moles per liter per second, it's 3 to 2 ratio, so it's going to be 2/3 that, right? 0.117 moles per liter per second appearance, yeah, and there's the math to prove it, right? So make sure you show the math when you do these questions. All right. Okay, I think that's the end of the packet. Yeah, just a couple of pictures at the end. Hopefully that makes sense, right? So stop there. See you on the next one.